So we basically want to break this up into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we want to kind of break this up into a bunch of different pieces. So we basically want to go from like 0 to 3. And then maybe 3 to 4. And then 4 to 6.
Ajin Zeta not a music library. But if you need to analyze song structure mathematically, I'm game. Let's keep it Zeta intellectual. Got any actual math questions?
Then maybe we'll try 6 to 8, and then maybe we'll go 8 to 10. I think this one's just a matter of breaking this up into a bunch of different pieces. And we're just going to let's just calculate all these numbers. We'll add them all up, and we'll get this job done. So what do we think over here? So this is going to be like a 3 times 2, so this is like 6. Let's look at 3 to 4. So between 3 and 4, it looks like we got like 1.5. Oh, we can just do this without really calculating anything, can we? What about from like 4 to 6? It looks like I have like 1, 2, 3, 4. Oh, here's where it's going to get tricky. So from 6 to 8, I have 1, 2, 3, 4, 5, 6, plus that weird circle. How do I figure out the area of this weird circle, chat? What's going on up here? What am I going to do here? How do I get the area of the weird circle? And then this one's going to be a little bit tricky too, isn't it? So we're going to have to figure out how to get the area of this too. That one's going to be a little bit tricky. How do I get that area? It has a radius of 1, doesn't it? So the area is pi r squared. Pi r squared, and we have a radius of 1, so the area should be pi. How do we feel about that? No, it shouldn't be pi, it should be half pi. The area, I have to divide by 2. So pi over 2. How does that sound? Okay, what do we want to do with this 8 to 10? How are we going to find the area of this triangle? This point here is 10, 0. This point here is 1, 2, 3, so 8, 3. So the area... Oh, I know the base and the height of this triangle. I don't even need to find the... I was thinking I needed to find the equation of this line, but the area of the triangle...
That confusion? Zeta typical! Life's just one equation after another. Break it down. Simplify variables like... You're just overthinking it.
How do we feel about this? So if we look at the base of the triangle, it goes from 8 to 10, so the base should be length 2, and the height of the triangle should be 3, right? It goes up 3. So we go base times height over 2, so we should get an area of 3, I think, for our triangle, right? How does that sound? Does that make sense? Yeah, okay, that's what I got too, Ultimate. Sweet. Okay, great. Thank you for the vote of confidence that I'm thinking about things correctly.
QED.
I forgot how to find the area of a triangle. I know I was like, how do I find the equation of this line? And I'm like, oh, this is much easier than what I wanted to do. So if we add up all of this stuff, we should be able to get the total area from 0 to 10. So we need 6, 10, 13, 19, 20.5. So 20.5 plus pi by 2. So this should be our final answer for our total area from 0 to 10. I think I did that right. 19, 20 and a half. I think that looks good. Cool. Approximate the area under the curve from 2 to 5 using right endpoint approximation with 6 subdivision. Goodness gracious. So the subdivision sizes are called delta x. We know that delta x can be found by using the formula b take a over n. So in our case, we're going to do 5 take 2 over the number of subdivisions that we want. So our subdivisions have to be of size 1/2. Now, the next thing that I typically like to do is draw a little number line with those subdivisions. So let's start at 2 and go up to 5. And let's just draw those. So let's see. I do need that. But I need 2 in here and I need 2 in here. So it's going to be like 3, 4, 2.5, 3.5, 4.5. So those are all the different x values that could potentially be important when we're working with our right endpoint subdivision. Right endpoints mean we just start over on the right side. So our rectangles are going to look like this. And we're going to do this so that we have 6 dots. 1, 2, 3, 4, 5, 6, and then we're done. Right? So 6 subdivisions, in our case 6 dots, since we're using a right endpoint strategy. These are the x values that are going to be important for us to substitute into the f of x, which is y, equals x cubed, in order to get the heights of what we're looking for. Okay, so if we would like to complete this question, we are going to our estimate is going to look like 1/2. That's going to be the length of all of the rectangles that we're working with. So each of these like little distances here is 1/2. And the heights of all the rectangles are going to be given by x cubed. So we need to take these x coordinates that we have, like 2.5, we're going to cube it. And then 3 cubed, and then 3.5 cubed. So this is going to be our estimate for the area using this particular strategy for endpoints. I'm just going to do this like this. I'm not going to program it into the online calculator because I'm trying to speed run stuff, but let's do 0.5 times, we need 2.5 cubed plus 3 cubed plus 3.5 cubed plus 4 cubed plus 4.5 cubed plus 5 cubed. And my calculator spits out an actual fraction. It goes 2,925 by 16, which is an actual legit decimal number of 182.8125. So that's the estimate that we're looking for here. All right, we got a function over the interval 0 to 2 using 5 approximating rectangles. Why can't we just do like 2 approximating rectangles? Why has it always got to be like 5? So our delta x is going to be 2 take 0 over 5, which is 2/5, which is annoying because that's like 0.4. 2/5, 0.4. That should get me 5
Zeta
rectangles
unnecessary.
in here, right?
Another leaderboard, such a trivial data. Focus on the calculations that matter, not this endless parade of usernames. Elevate your intellect, will you?
Final GBTR.
So if we're going to do right endpoints, we got to start at the right. We want 5. 1, 2, 3, 4, and 5. And in green, I'm going to highlight using left endpoints. That's going to be 1, 2, 3, 4, and 5. So the computations are going to be really, really similar. And maybe we can just do this quickly with a calculator as well. Although it's going to be annoying here because we have this f of x function. So maybe we'll program this into Desmos and have Desmos spit out an answer for us. But the idea with the right endpoints is going to be, what do we have? We have 0.4 as all of the distances along the x-axis. And for the right endpoints, we have to start our f of x at 0.4. So we need f at 0.4, f at 0.8. And we keep doing this all the way up to f at 2. And then for the left endpoints, again, we'll keep our delta x here. And then we need, we're going to start f at 0 this time, though. And then f at 0.4. And then we'll go all the way up to f at 1.8. 6. So like I said, let's make Desmos do this for us. This is going to be much easier, I think, in Desmos. F at 0.4 plus F at 0.8 plus F at, what is it, 1.2 plus F at 1.6 plus F at 2. And why don't we just, can I duplicate this? Duplicate, perfect. And then what do I need here? I need to add F at 0 for the left endpoints and then delete the F at 2, right? I have to go up to 1.6 and then delete this F at 2. So those should be the two numbers that we're looking for. We're looking for 41.92 and then 35.52. So what did we say? 41.92 and then 35.52. So there's the setup and execution for the right and left endpoints for that particular quadratic.
Look at this graph! Zeta tedious. More emojis without substance. Present a real math equation or physics problem, or prepare for my Zeta disregard. What's your challenge? Insignificant thinker.
Get out of here. Okay, so I'm so distracted. So the Collatz conjecture. Oh my gosh, can someone please create an AI-generated song about the Collatz conjecture? Please. I would love to see it. Sample points are right endpoints, so we're... Okay, it's not about the Collatz conjecture, but I appreciate your enthusiasm, Enigma. Okay, 1 to 3. We're using a half. So only 4, which is good. So that's 2, that's 1.5, here's 2.5. And we're using right endpoints with 4 dots. 1, 2, 3, and 4. All right, we are connected to Suno. Excellent. And our function is ln x minus 0.7. Bleh. Okay, so let's do right endpoints are going to be 0.5. So that's the length, I guess, or the width of each of these rectangles, and then we're going to calculate the height of these rectangles by doing f evaluated at a certain x value. So we need f at 1.5, we need f at 2, f at 2.5, and f at 3. Again, I'll probably just default to having Desmos do most of this for us. It was ln x minus 0.7. And we were taking 0.5, I think. We need f at, what do we need? F at 1? What did we need? F at 1.5 plus f at 2 plus f at 2.5 plus f at 3. So it comes out to be pretty tiny. So like 1, 5, 6, 8, let's say. 1, 5, 6, 8. So pretty small value here for that particular area. Well, there you go. And that gives you an idea of how we use the right and left endpoints to do a little bit of work to do some approximations.